Welcome to lesson number 10. This is the final lesson for this unit. We're going to talk about the unique factorization theorem and just how to use it. We talked about it a little bit in lesson 7, but remember we were only using it with coefficients of 1 or negative 1. Now, the theorem has 2 points that you need to remember. So point number 1 is that every polynomial function can be written as a product of its factors and a leading coefficient. Now remember, sometimes that leading coefficient is 1, in which case we don't really place it in there. We just make the assumption that it's 1. And then point number 2 is that every polynomial function has the same number of factors as its degree. So if it has a degree of 2, then that's how many factors it's going to have. And the factors may be real complex or may also be repeated. And when we have them being repeated, that's where we talk about the multiplicities of our coefficients, or sorry, of our factors. All right, so let's look at this first example. The graph of a third degree polynomial function p of x is shown. So there's 3 degrees here, and the graph has integral x-intercepts and passes through the point 2 and negative 24. Now explain why the equation of the polynomial function can be written in the form c of x, x plus 1, and x minus 3. Well, it can be written in this form because there's actually 3 distinct zeros. We have 0 right here, x plus 1 we have negative 1, and then x minus 3 we're at positive 3. And the reason we can write it like this is because, well, we have those 3 zeros. There are 3 zeros, and the other reason we can write it like this is because they have a multiplicity of 1. And I know it has a multiplicity of, each one has a multiplicity of 1, because if we look at the line itself, it's only passing through the x-axis. It's not tangent to, and there's no points of inflection in this case. All right, so let's look at part B here. Use the point 2 and 24 to help determine the value of c, and hence write the polynomial in expanded form. Now, when we start these, remember that we're looking for this coefficient. And so sometimes that coefficient is going to be 1. So x plus 1 and x minus 3. I'm just using the above polynomial expression up top. And we're told that it goes through the point 2 and negative 24. And so 2, that's my x value, and that's my y value. So I'm going to plug those into the appropriate places in the equation. And anywhere I see the value of x, or the coefficient, or the variable x, I'm going to replace it with 2. Now what I'm going to be left with here is 2 minus 3 is negative 1. Negative 1 times 2 plus 1, which is 3, is negative 3 times 2 is negative 6. So with negative 6c, and we get a value of c equal to 4. This means that I can rewrite my expression as p of x is equal to 4x times x plus 1 is x minus 3. Now, this isn't exactly expanded form yet. If we want to write this in expanded form, then we don't want to show any of our factors here, right? And if I don't want to show any of the factors, then what I want to do is distribute this 4x into everything. But before I even do that, I think it's a lot easier if we simplify this middle term. And so what we're going to be left with here is x squared minus 3x plus x, which was minus 2x minus 3. And finally, if I distribute my 4x into each of these, I'm going to be left with 4x cubed minus 8x squared minus 12x. And that is not a plus sign. That should be a negative sign. All right. So there we have the leading coefficient as a 4. All right. Now let's look at this next example. So the graph represents a polynomial function of lowest possible degree. The intercepts are integers. Determine the equation of the polynomial function in factored form. All right. Now we know we're looking for something like this. P of x is equal to c of x of the factors. Now there are some assumptions that we want to make, right? We want it to be in lowest possible form, and we know where our zeros are. We have a 0 at negative 2, and we also have a 0 at positive 2. and there's only the 2 zeros here. And so I know that it's going to be, if it's positive 2, and this is linear, or not linear, but it's only crossing my line at the x-axis, we know that that's going to be a multiplicity of 1. So that'll be x minus 2. And we know that this factor at negative 2 is going to be x plus 2. But notice how there's a point of inflection. Remember, the points of inflection occur at odd multiplicities, and we want the lowest possible multiplicity, so that means that it has to be 3. And remember, in this lesson, we're looking for the leading coefficient that's other than plus or minus 1, so we know that we're going to have to be solving here for C. Now, if I look at this question, I'm not given any points that this line goes through. And so what we can do is we can always find one of the points that goes through, whether it be the x-intercept or a y-intercept. Now, it's probably better, well, it is better to use the y-intercept because this goes through 2 x-intercepts, right? It goes through negative 2 and positive 2, which won't be too helpful for us. Now, what I'm going to do then is I'm going to find out, well, what is this point here? Well, remember what we did yesterday is we found that if I have a multiplicity and so I raise my factor to the power of its multiplicity, 2 to the power of 3, that will give me the y-intercept. And remember, the y-intercept is always going to be when x is equal to 0. And so that's what I'm going to do here. I'm going to choose the y-intercept, and that's going to be at 0, and 2 to the power of 3 is 8, but remember, it's going to be negative 8. And so now I can plug that into my equation, and wherever I have an x, I'm going to replace with a 0. So I get 8 times 2 times negative 2, and that'll be negative 8 is equal to negative 16c. If I divide both by negative 16, I'm going to be left with 1/2 is equal to c. And all I want to do is determine the equation in factored form. So this is going to become p of x is equal to 1/2 x minus 2 x plus 2 cubed. And that would be my final answer. Alright, next, determine the equation in factored form of a 4th degree polynomial function which passes through 1 and negative 2 and is tangent to the x-axis at 2, 0, and at negative 3 and 0. Now, there's a few subtle hints that we can pick out of here. We know it's a 4th degree polynomial. And it passes through 1 and 2, and is tangent to 2 and 0 and negative 3 and 0. So what this tells us is if it's a 4th degree polynomial, then it's going to have even exponents. And if it's passing through 2 and 0 and negative 3 and 0, that means that these are our zeros, right? If it's tangent to, it looks something like this. It looks something like that. And so that would be at 2, and this would be at negative 3. So it's not crossing the line. And remember, if it's tangent, that also means that it's even multiplicities. And so I know that then both the zeros are going to be squared and have a multiplicity of 2, right? So this is going to have a multiplicity of 2. So I know I'm looking for p of x is equal to c times x minus 2, and that's squared, times x plus 3 squared. Now, in this case, I'm given the actual point, and so I can plug that point in and solve for all the values that I'm given. So I'm given x and I'm given y, and now I can solve for c. So negative 12 is equal to c. 1 minus 2 is negative 1 squared is just 1. 1 plus 3 is 4 squared is 16. So negative 12 is equal to 16c. Oh, sorry. And if I solve for c, c is equal to negative 12 over 16 or negative 3 over 4. And so if I plug this into my my polynomial expression left with negative 3 over 4 times x minus 2 squared times x plus 3 squared. All right, now I'll just run through these last two examples a little quickly. If we look at the fourth degree polynomial, it passes through the point 1 and 2 and has zeros at 1, negative 1, 0, 3 halves, and 2. I want to determine the equation of p of x in factor form using only integral linear factors, so I don't want to have any fractions in this case. Now, if I have, it's a fourth degree polynomial, and I have 1, 2, 3, 4 zeros, that means that all of these have a multiplicity of 1, which makes it easier on ourselves. 4 zeros all have a multiplicity of 1, and since I have 0 there, it's going to be c of x. And I'll be with x plus 1, 2x minus 3, and x minus 2. And I'm told it goes through the point 1 and 2. And so 2 is equal to c times 1 plus 1 times 2 times 1 minus 3 times 1 minus 2. C is equal to 1 times 2 times negative 1 times negative 1. 2 is equal to negative 1 is 1 is equal to 2c. C is equal to 1. Now p of x then is equal to x times x plus 1, 2x minus 3, and x minus 2. Since my coefficient was 1, we don't have to include it there. And this last example, a polynomial expression has the following three roots, or zeros, negative 2, and that has a multiplicity of 1. And we're looking for the coefficient, so I'm just going to put c. There's no, since there's no 0 at 0, I can just say c bracket, and since negative 2 is a root with a multiplicity of 1, that means it's not going to have any exponents on it. I have 1/3 as a root with a multiplicity of 2, 3x minus 1, that has a multiplicity of 2. And I have 1 as a root with a multiplicity of 3, so that's going to be x minus 1 to the power of 3. And the graph of the corresponding polynomial function has a y-intercept of 2/3. So plug in 2/3 and we solve for c. And since that's the y-intercept, that means that it's at 0 and 2/3, which means that 0 is the value of x we're going to use. So wherever we have a value of x, we're going to replace with 0, and we're going to be left with 2/3 is equal to c 2 times negative 1 squared, negative 1 cubed. So that'll be negative 1, that'll be negative 2c, and c 2/3 divided by negative 2 is going to be negative 1/3. And so p of x is equal to negative 1/3 x plus 2 3x minus 1 squared and x minus 1 cubed.